So now we are thrilled to move along to our final segment tonight. We're thrilled to have Dr. Paul Byrne join us and talk about Venus. Paul, are you there? There you are. Welcome.
Hi, everybody.
Welcome.
Can you hear me okay?
Absolutely. You sound great.
Awesome.
So we're excited by some Venus announcements, and I'm going to give a very brief rundown here about what we know about Venus, what we've been doing. So first of all, Venus, it's that bright planet in the sky. It's in the evening sky. It's in the morning sky. It's known as the morning star. Sometimes it's not a star. It's a planet. That's the moon, of course, near it, the crescent moon. When you look at Venus through a telescope, it actually goes through phases. It can be a crescent. It can be a gibbous. Yes, it has to be on the other side of the sun to be a full Venus, and that's kind of hard to observe it there. But notice, it's really cloudy. You don't see the surface easily. It's basically the same size as Earth, very, very close to it, but it evolved differently. It's only about, what, 70% of the distance we are from the sun. So not that much closer to the sun, and yet it's hot enough to melt lead on the surface of it. Even with all those thick clouds, you might think clouds, it's blocking sunlight. No, other way around, like climate change, it's holding in the heat. Earth has a moon, Venus doesn't. Very, very sad about it. And that might have something to do with why the way we are and the way Venus is, but we need observations to find that out. Mariner 10 flew by, took some pictures of Venus. This is in the ultraviolet. Again, we're not seeing the surface there. So NASA designed the Magellan spacecraft. We're skipping a bunch of missions to Venus, by the way. I'm just skipping right over them. But Magellan was a super interesting mission. It had radar mapping built in. So when it got to Venus, it was actually able to see things like volcanic peaks, which are interesting. Those are not glowing red due to lava. That's just colored for height. Here's a color of sort of the continents, or a map of the continents of Venus. Indeed, it seems to have sort of structures that look a lot like our continents, but were they formed in the same way? We just don't know. Very little information is there about them. The Europeans sent the Venus Express mission there, and indeed, it saw signs that there were temperature changes happening on the surface that might have been consistent with active volcanism today. Wouldn't be super surprising, but I don't know if I believe it completely. It seems compelling, but I want more data. More data are always better. Volcanoes on the surface, can we see those? Is that something to believe? I don't know. Well, why are we even talking about this? I think it was 2-3 days ago now, new NASA administrator made the announcement that they'd chosen which are the missions that are going to be the next big flagship missions, and 2 were chosen to go to Venus. VERITAS was one, and the other is called DAVINCI Plus. So, Paul, why are you excited about this? Dr. Byrne, you study planetary planets. You look at Earth analogs, I know. You look at places on Earth that are sort of like places out in the planets to figure out what happened, and you want to compare Earth to there. But, you know, why are you so excited about this? What is this going to mean for our exploration of Venus? And, you know, why should we care?
Okay, well, so here's why we should care. So thanks, David, and it's a pleasure being here with all of you, and I've really enjoyed the show so far. It's all underpinned by a single question, and like you said, Venus orbits about 3/4 as far from the sun as we do. It's about the same size, and it's made of about the same stuff in about the same proportions. It goes around the same star, and it's the same age as Earth. So how is it that you can have another large rocky world just next door that for all the world is our sibling planet, but it's not our twin? That is the crux of the question for Venus. However you want to phrase the specific science objectives and questions you have about its climate and about its interior, how do you end up with a planet that looks so weird and different compared to Earth? And there's a couple of reasons why this matters. So I'll talk about this in a minute. We have 2 leading models for how Venus got the way it did. And we don't know right now which of those 2 models is correct. But the reason this has taken on, this has always been interesting. And since we discovered back in 1962 with the first successful interplanetary flyby by the Mariner 2 spacecraft, which up until that point, up until certainly in the 50s, people were writing science fiction stories set on Venus, where this was a lush, tropical, rainforest-like world, because the assumption was it was that little bit closer to the sun, and therefore it was just a little bit warmer. And then Mariner 2 in 62 put pay to that. It was like, no, using radio waves, it was able to determine that the surface or the lower atmosphere of that planet is scaldingly hot. And David, you described it as being hot enough to melt lead. I have to confess, I have absolutely no intuition for the temperature required to melt lead at all. So when I talk about it, I say it's the same temperature as a self-cleaning oven, because I know that when my self-cleaning oven is on, I don't go near that thing. That is the kind of prevailing regular temperature at Venus. The point is that
there is a crazy man that has hacked his oven that he can bake in it on the self-cleaning cycle because he wants to make Neapolitan pizzas. So,
you know what? I mean, and to be fair, that would be quite an effective way of doing that. You would get that for free on the surface of Venus. Of course, you'd have no capacity to eat the thing because you would be dying. But the point anyway is that we've known for 50 years that Venus is a world right next door and is quite unlike our own. But the reason this has taken on a particularly special, I guess, significance in the last, let's say, 10 years or so is we're now getting into looking at these extrasolar planets, these exoplanets, right? And right now, in terms of our capability with our modern telescope technologies, we cannot resolve the difference in size between an Earth-sized world and a Venus-sized world in orbit of another star. So anytime you hear a press release or you read a press release about, oh, an Earth-sized world found somewhere, you may as well replace it with Venus-sized world. It means the same thing. Yeah. And when someone says Earth-like, they're lying, because we have no definitive evidence that an Earth-sized world is necessarily Earth-like. In fact, it could be Venus-like. Mm-hmm. And if we don't understand why Venus ended up the way it did, or let me put it this way, why Earth has ended up the way it is, we are not going to have a framework or context for making sense of what we see around other stars. Right? So that's why this matters. This matters for a bunch of reasons, but that's the most important one, I think. If we're serious about looking for life on other worlds, looking for habitable conditions and understanding what planetary habitability means, we're not going to find it on asteroids. I personally, and I would happily come back for another talk about why I think the ocean worlds in the outer solar system are sterile. We're not going to find it in these small worlds. Mars, we think, may have been habitable for a long time, but it was never habitable the way Earth was. It simply was too small. We have one of these two models for Venus says that it may have had liquid water oceans for 3 billion years. So we need to understand if trees and squirrels and beaches or a self-cleaning oven is the outcome we can expect for large rocky worlds. And we don't know. And the way we're going to answer that question is we're going to go back to Venus.
Well, now, why do you think these missions are going to tell us about that? What capabilities are they going to bring to this problem?
All right, so I want to kind of just presage my answer by saying this. No 1 or 2 or 5 missions is going to solve Venus. That's just not going to be how it works. That's not how it's worked for Earth. We know from 25 years of sustained Mars exploration that we still don't really understand Mars all that well. We still have major questions to answer. So these missions are not going to kind of, put Venus in a box and we can move on. But they are going to help us take 2 major advances forward in understanding Venus. But I will also say this. I promise you, in 10 years, when we're starting to kind of work through the consequences of what these missions have told us, we will have whole new questions that we don't have the imagination to ask yet. So it's going to get worse. Our understanding of Venus will in a way get worse when we start getting a better understanding of it, but that's how it always goes in science. Okay, so let's take VERITAS first, which is the image I think we have up right now. VERITAS is a radar mapper. So you've mentioned that the reason Venus is so bright in our sky, its albedo is about 0.7, right? So it reflects with 70% of the sunlight it receives. That's because it has this global layer of H2SO4 clouds, of sulfuric acid clouds. So that's one of the many ways in which Venus will try to kill you if you go near it. And the point about these clouds, it's this cloud layer, like you said a minute ago, David, that's retained that heat. That's basically, it's both a consequence of and a retainer of what we call the runaway greenhouse effect on Venus. That's why it's so hot. Venus, the surface temperature is the highest of any of the rocky worlds. And so it's fact that it's the hottest surface in the solar system, hotter than Mercury, because Mercury is only heated by solar radiation. It doesn't have an atmosphere, it doesn't have a climate, and it's the climate that's doing it to Venus. And the reason that matters is because you cannot therefore look at a planet and look at its distance from its parent star and just assume you can measure it, you can estimate its temperature. That we now know that doesn't work. So what basically the way we try and see, the way we are going to see the surface, the way we have in the past seen the surface of Venus, is we have to use radar. Radar can penetrate through that thick cloud layer, just like we've used radar to see through Titan's thick hazy layers, Titan's Saturn's biggest moon. So we've had radar measurements The United States sent the Magellan mission. In fact, the Soviets, Vega 15 and 16 missions also carried radar, although they weren't as capable. So we know kind of to first order, right? Top of the line, we kind of know what the surface looks like. The problem is that the resolution of those data are very limited. They are comparable to perhaps what we had from Mars after the Viking missions in the 70s. That was enough for Mars to give us a sense of what the overall story is, but we missed an awful lot of details, right? We missed a lot of details. There's a lot of fine stuff you cannot see with that kind of resolution. And when we went back in the 2000s with much higher resolution, much more capable cameras on Mars, we came to learn a new world. That is what VERITAS is going to do. We have some key questions right now we cannot answer with the currently available data. We are only going to be able to actually test our hypotheses and refine our ideas by getting back there with much higher resolution data. And you're showing here some of the SAR resolution. So SAR is synthetic aperture radar. It's the type of radar that Magellan carried, 150 to 280 meters. The kind of global mosaics were downsampled to 75 meters per pixel. They really weren't actually that high, and that's still pretty coarse, because it takes about 3 or 4 pixels for anything to kind of come into form. So you're not seeing objects 75 meters across, you're seeing objects maybe 250 meters across. You're seeing maybe a football field, or maybe several football fields. That's like the smallest thing you can see. So again, you're going to see where all the big things are, but you're going to miss an awful lot of detail. Whereas VERITAS is going to have the ability in places to take resolution images as sharp as 15 meters per pixel. When we had that resolution at Mars, suddenly that began to just show this whole new world for us. So again, I do not have the imagination to predict what we are going to find, but it is going to allow us to understand that surface and its history way better than we do now, right? And one of the things we're going to look at is, what is the history of how the surface came to be the way it is? One of the most strange and surprising things that Magellan told us back in the early 1990s is that there's fewer than 1,000 impact craters on Venus. And that is weird, because look at the moon through a telescope, right? It's pretty easy. You get to 1,000 pretty fast. There are no craters smaller than 3 kilometers in diameter on Venus, because the atmosphere eats up things that would make craters smaller than that. But there are no gigantic craters on Venus either. There are no basins like Oriental or Imbrium or Tranquillitatis or Caloris and Rembrandt, or what the hell else is out there? Hellas, Argyre, Utopia, Isis. Like, you just don't have those giant basins on Venus. Now, surely Venus had them. The moon has them. Mercury, Mars, right? Earth had them. On Earth, they're gone because of plate tectonics. Now, we don't know why they're gone on Venus. We do know they're gone, which means that less than 1 billion years of history, well, actually, that's a big unknown as well, but we think less than 1 billion years of history is preserved from the surface of Venus. That's not much of a record as planets go. VERITAS is going to be able to help us tell not just what's there topographically, but also from this image here, VERITAS is going to carry, for the first time, a capable spectrometer that is going to be able to actually tell us the spectral characteristics of the rock. It turns out that when I said you can't see the surface from space, I kind of lied. There's a few windows around 1 micron or so in the infrared that you can see through the atmosphere, and you can there's a lot of issues. You get scattering in the atmosphere, so the resolution's poor. But for the first time, VERITAS is going to actually try and tell us something about what the rocks are made of. It won't definitively say it's this rock and it's that rock type, but it will be able to tell us where the differences are. And then on the basis of lab measurements we already have and will continue to get, we can start making educated guesses about not just what the rocks are, but how they change in space. And because VERITAS is going to give us really powerful control in the 3D, in the third dimension, us geologists rely on that to get timing, right? Stuff that's sitting on top of other stuff. So in 10 years, when VERITAS flies and starts returning these data, we are going to learn of a new world. And a lot of our existing models for Venus will be proven to be wrong. We'll develop new ones, and we will realize just how complex, and I suspect, by the way, dynamic. So David, you were saying a minute ago about volcanism. I am absolutely positive there are volcanoes erupting right this second on Venus. In fact, I would eat my desk, preferably if it's made of chocolate, if we find there are no active volcanoes. And there's a few reasons for that. And the fundamental one is this: how is it you can have a world about 85% the mass of Earth and not have it be volcanic? Earth is erupting all the time. And I don't mean the eruptions like in Iceland. And I mean the seafloor spreading volcanoes, right? The vast majority of volcanic activity takes on the ocean floors. There's no way that's not happening on Venus. There are tens of thousands of volcanoes. There are probably millions of discrete volcanoes on Venus. We just can't see all of them. And we have a global layer of H2 of SO4, right? This is sulfuric acid. H2SO4 is made of H2O and SO2, two of the three dominant things that comes out of a volcano. The cloud is not chemically stable over billion-year timescales, which means it's either new or it's being replenished. And the only way I can think of doing that is volcanoes. We know there are some very, very young, geologically young flows, because we know that from the radar data. They've got very fresh edges. There's no way that thing isn't erupting right now. And there's no way it's not tectonically active right now either. It doesn't mean plate tectonics, but it means stuff is moving.
Yeah.
VERITAS is going to be able to tell us that.
Okay. Now, I remember way, way, way back from, gosh, even undergraduate. So this is decades ago. There were folks talking about how Venus might resurface itself globally every so often. Is that still
no, that's wrong.
Idea?
That's wrong.
That always seemed a little false to me.
Yeah.
I thought it should be more like Earth with plate tectonics in a continuous process versus something that's sort of like we're all lava now and now we're all solid.
Yeah, so there were some bad ideas that were developed back in the day. And the problem is that there wasn't very much a way of new data to kind of test them, right? Yeah, the reason that global resurface is, let me be very clear for folks who are watching, right? So we do know that there's a weird dearth of craters. And we do know that the average surface age, on which we estimate from cratering records, right? So this is a whole other conversation, but the way we get ages from craters is it's assumption based upon assumption based upon assumption, for, sleight of hand and a bunch of it is a precise but inexact science. So if someone tells you something to more than two significant figures, they're lying in terms of age, unless and until we get there and sample stuff. But the surface of Venus on average is younger than 1 billion years. But the thing is, we don't quite know if the bell curve of ages is like a really tight one where they're all clustered around that age, which is what the global resurfacing model will have you believe. Or if in fact the bell curve might look a bit like this, and there are some parts of the surface that are really young and some parts that are really, really old. And I mean billions of years old, but we don't know. However, if you look at different areas, unless you assume spatially disparate places that look sort of the same are in fact the same layer, which we never do on Earth, you cannot find support for that global vomiting of lava. I mean, that's what I learned as a kid, right? That this thing every 750 million years has vomited itself out. And that is consistent with the observations, basically. But it's geologically wrong. This thing is probably just, in fact, this is very hard to measure because the data we have at Magellan don't really help us test this. It's probably likely that the rate of volcanic eruption is about the same as Earth proportionately. And it's coming out, like you said, in sort of splotches. VERITAS, through repeated imaging, is going to be able to, with the resolution it's going to be able to get, will allow us over, we know what the modern impact flux at Mars is, because we can take images with Mars Reconnaissance Orbiter and see new craters form. And we miss a few, sure, but we can spot them. And you can go to Google and image, the same land, 6 years apart as a new crater in it. We won't probably see new craters at Venus because, like I said, you don't get a crater smaller than 3 kilometers, and the things to make things that 3 kilometers and above are pretty rare. But we might see a change in a lava flow or a new lava flow. That's the kind of thing that goes straight onto the cover of Nature or Science, because it would be the kind of smoking gun we don't yet have to understand whether there's active volcanism on Venus, which of course there is, but we don't know for sure. So that's one of the ways. So VERITAS is going to tell us what modern Venus looks like and going to help us look back in time by seeing what's preserved from the surface. Then you get to DAVINCI Plus. And DAVINCI Plus is a different thing. And one of the most exciting aspects of the announcement 2 days ago is that we're going to get 2 missions, but they do 2 different things that are all part of the same kind of story, which is understanding present Venus and understanding its past. Now, DAVINCI Plus, the star of the show, it has an orbiter as well. So VERITAS is a fairly capable big orbiter. DAVINCI Plus is a smaller orbiter, but the star of the show is this big meter-wide sphere of metal. And it's going to be dropped down through the Venus atmosphere. And you can see this image here. This is what we call the entry, descent, and landing phase, or the EDL sequence. Now, the EDL sequence for Mars probes, particularly for Curiosity and Perseverance, features this just bananas sky crane, SWAT team helicopter maneuver, right? This photograph is a little misleading because what you can't really see is, you'll notice the second last thing from the bottom, it's the little ball, is the little sphere is still on its parachute. The way you actually get to the surface, now the probe is designed to operate during its fall, during its transit to the atmosphere. It's not a lander. It's not designed to survive the landing. It's not expected to. It probably will, because these things tend to be extraordinarily well engineered, but it's not, there's no plan for it to operate on the surface. So if you get a picture on the surface of this thing, it'll be lying on its side and it'll be bonus, right? And it'll die 20 minutes later because the surface is self-cleaning up. But unlike what this photo suggests, this thing is not coming down on a parachute all the way down, because if it did, it would overheat too fast. One of the keys for operating anything with modern technology is that it cannot spend that long going through the atmosphere or it overheats. So the way you get to the surface is you come in on your heat shield, and then you blow the heat shield away, you get rid of it, you come on, you got your back shell, your drogue chute comes out, then you'll pull that away from whatever else is the structure around you, then the main chute comes out. But when you get to an altitude of 60 kilometers, you drop your chute, you just cut it off, and you free fall. Because getting to the surface of Venus is much more like getting to the surface of the ocean floor than it is anything else. So this thing's going to free fall ballistically for 60 kilometers. It will take about an hour, about a kilometer a minute, as this thing just gets hotter and hotter and hotter. On the way down, it's going to do two important things. It's going to take at regular intervals, it's going to ingest a little bit of the atmosphere, and it's going to measure the composition of the atmosphere with onboard sensors. And those sensors are going to measure specific compositional things, particularly the abundances of noble gases. And I'm going to skip over the detail of why, except to tell you this. Measuring what the composition and abundance and ratios of different noble gas isotopes will tell you extremely precisely what basically the history of volcanic degassing and even how much water Venus is born with. And those two, I referred earlier to the fact that there's sort of two models for Venus. One is that Venus was always ruined. It started off with that runaway greenhouse effect from what we call the magma ocean phase. It was just too close to the sun. It was never able to cool down. It was never able to condense any steam in its atmosphere to oceans. It was just wrecked from the beginning. That's model one. Model two is that it's possible, and really exciting work in the last 13 months has started to kind of add a new dimension to this discussion. It may be that if you are able to protect yourself with a hemispherical cloud, you might actually be able to get out of that early tumultuous phase. You might have enough ability to reflect light that you can prevent the runaway greenhouse effect being triggered from that early time when you're really hot. And once, if you get out of that phase, which Earth did, then there's no reason you can't condense the steam in your atmosphere, develop oceans, have a nice, well, we don't know the composition of the atmosphere, there's processes that play into that, but that's the scenario that gets you to the point where maybe Venus is habitable. And we know, for reasons I'm going to skip, that Venus had a lot of water in its past. We don't know if that water was steam, which is model one, or if it was liquid water, which is model two. VERITAS, or rather DAVINCI, as it goes down and is sampling the atmosphere and measuring those noble gases, the aim is to be able to tell, simply from the measurements it will take over 60 minutes, that's all. It's going to be able to put a pin in which of those two models is correct. It won't answer everything, but it will tell us which model is the right one, or probably some weird third thing we haven't thought of yet. But the point is, that's what DaVinci Plus is going to do. Now, there's more cool thing it's going to do. As it's falling, remember, it's not designed to operate on the surface, but it is going to get there. It's like, anytime a plane takes off, that plane is coming down again, whether it's going to be controlled. No. Same with this probe. This probe is not going to go back up again. It's going to hit the ground. They've targeted it onto a type of terrain that we call tesserae. Tesserae is not a geological term. It's a term that Russian scientists invented in the 80s to describe these really, really weird looking, mucked up terrain that it's really tectonically deformed. It's folded, it's crunched. It just looks really weird. It occupies about 8% of the surface of the planet. We don't know what the tesserae are. If someone says we do, they're lying. We don't even know that all the different parts of the planet where Tesserae is exposed is the same kind of rock, because the word is simply a way of describing the morphology of this material. There's no independent evidence that it's the same rock everywhere or it's the same age everywhere. Like, legitimately, when you people ask people, well, what's the most interesting thing about Venus, or from a geological perspective, where would you most likely to go? They'll tell you tesserae. Now, we've never tried, and by we, I mean human beings. There's only been about 6 or 7 successful landers ever on the surface of Venus because of how difficult it is to get there and operate there. They were the Soviet Venera landers and then the Vega landers in the 70s and 80s. Those landers touched down on the relatively smooth expanses, which occupy about 80% of the surface of Venus, which we know are basaltic lavas. No one's ever tried to land on the Tesserae because we don't know. We do know that they're really rough from radar data. We don't actually know what they look like, because of course radar data are not the same as looking at Google radar images and then Google the same area in Google Earth or maps, and it doesn't look quite the same. So we don't know what the Tesserae look like, and we certainly don't know what they look like at the scale of a lander. So we don't know how to build a lander that will be resilient to a Tessera, because what you really want to avoid is spending a lot of money on a thing and then it kind of lands and then tips over, and then the radio antenna is pointing to the ground, and then your mission is just not going to work. DaVinci Plus is going to take nested photographs for the last few kilometers. As it's coming down, as the haze starts to clear, this ground that it's going to be meeting is going to start swimming into existence. And it's going to be taking these photographs at ever higher resolutions. And those photographs are going to, provide unprecedented information on the geology of this weird kind of rock, or at least this particular exposure of it, and is going to provide critical data that we'll be able to use for engineering purposes to later in the future, in the next decade, develop a lander that would safely land on the Tessera.
Well, super interesting. I had a question, and we have a question from our YouTube chat as well. Is there any chance that the DaVinci probe could hit a portion of Venus's atmosphere that would just be unlucky, a little bit like the Galileo probe did on Jupiter, where they think they just hit a dry region?
Right.
Could that happen, or is this global enough we're not worried?
So, okay, to be fair, it's probably not a problem. We don't actually know definitively quite what the dynamics are in the Venus atmosphere. We have some hints from the Japanese, the JAXA Akatsuki probe, which is currently operating and has been there for 5 years in orbit of Venus. It uses infrared and UV cameras to see through different layers in the atmosphere. We get a sense of what the vertical mixing, what the horizontal dynamics are. But it's on a much larger scale than what a probe would experience, right? So it's not the same as, say, flying. You can look at a hurricane from orbit, but you want to get the hurricane hunters in there to actually get that high resolution data. Our current thinking of the Venus atmosphere is that somehow below about 110 kilometers or so, that's a layer or a point we think is the homopause. And below that, we think that the atmosphere is totally mixed. And we don't know that for sure, but it's likely. And so the view is, for our purposes, because of the vagaries of the Venus atmosphere and because of how slow how slow the planet rotates versus the atmosphere is actually super rotating, it was much faster, but it's still not that fast, that we think there's a good chance that you're going to get a representative profile no matter where DaVinci Plus's probe goes in. Now, that is not to say, like I said a little while ago, despite how exciting these missions are, this is, in my view, it should be seen as the start of a new era of Venus exploration. These two missions are not going to kind of resolve every question we have. What is interesting is we actually don't know what the middle atmosphere is like. We do know that the only other place in the solar system that's functionally like Earth, that is Earth-like, is the Venus atmosphere. Between 60 and 55 kilometers, the temperature and pressure are basically room temperature. You'll asphyxiate quickly because it's all 96.5% CO2. Right. But if you had a mass scuba gear on or something like a firefighter wears, you could potentially stand on the gondola of a big aerial platform. In fact, there are concepts to do this where humans could wear shirt sleeves and operate safely out there. So you could operate a balloon, an aerial platform of some kind, using a lighter than air ship, and operate up there potentially for months. The Russians flew with their Vega missions in 1985, 2 balloons, Vega 1 and 2, a few days apart, that were provided by the French. And those balloons operated for about 44 hours and traversed about half of the circumference of Venus. Now, the reason they only lasted 44 hours, they actually lasted longer, but because the Vega mission was just this, basically the Soviets were like, we're going to go to visit Hades' comet, but we're going to go and use a gravity assist to Venus. Why don't we just carry some stuff to Venus? That's what they did. So they dropped these balloons and they dropped landers. But then the probes, which were on their way to the comets, went out of range, and so we lost tracking with the balloon. That's why they only operated for 44 hours. They didn't last very much longer. In fact, that's the same deal with the landers. That the longest landed operation, I don't remember which Venera it was 127 minutes. It probably lasted longer than that, but that's how long it had to see its orbiter before it moved out of range. They're modern technology, modern batteries, modern solar charging capabilities, modern Mylar and Teflon balloon materials. You could have a balloon up there for 6 months. The longest stratospheric balloon on Earth operated in comparable conditions for 2 years. So you could be up there for a while. And if you did that, which I think you should, you would build on the DaVinci Plus measurements by characterizing, are there variations in time? If you're up there for much longer than 60 minutes, you can take much more precision, right? Because you can take as many samples as you want. you might be able to measure a wider range of things. This is not to say DaVinci Plus is not going to be critical. It is. But I want to try and shape people's expectations. It's like how we've been doing Mars. Right? We build up. Each mission advances on the other, raises new questions and offers further opportunities to answer old ones. So what would be amazing is we get VERITAS to give us that new topography and image data, which we badly need. We get DaVinci Plus to give us compositional data of the atmosphere in the atmosphere, because you really won't get it without being in the atmosphere, and images of the tesserae. And then later you send more spacecraft. You characterize the rate at which the atmosphere is being lost. You characterize what the dynamics and the chemistry of the atmosphere writ large is by being in the atmosphere. You land on the plains and you sample with modern analytical capabilities what the rocks are made of. That would immediately tell you, in the course of 8 hours, you would learn 4 billion years of history. You land then in the tesserae because DaVinci Plus and VERITAS have given you improved data for how you design something to safely land in the tesserae. You eventually then look to try and get a sample of the atmosphere that you bring back to Earth for labs and analysis on Earth. And then eventually, maybe in the 2060s, I don't know, you look to try and bring some of the Venusian crust home, like we're beginning to do for Mars. This is how we do it. We do it in steps. It's going to be hard. It's going to be expensive, but they are not reasons not to do it.
Right.
But the way we get there is we build up decades worth of experience, plural decades, to understand how to do it. Because I cannot emphasize this enough. If we are serious about understanding how our own planet came to be and how it stayed habitable for 4.5 billion years and why it isn't ruined, we need to understand the history of Venus. That's the only way we are going to be able to understand our own world, both its past and its potential future, to say nothing of large exoplanets. It all hinges on Venus.
Yeah, well, and also Earth is undergoing dramatic climate change right now, and we're understanding that through Earth observing missions. But to have something understanding Venus and have that point of data, to have that datum there, it's crucial in my opinion. It is the more we know, the more we can understand what's happening on our own planet. Now, one question from our audience out there. Very technical question about the different bands that are used, and the question was, why was the X band chosen for the radaring system? Because the thought was it doesn't go through clouds very well. My thought was that would be Earth clouds the X band doesn't get through, that it penetrates Venus clouds just fine.
That's right.
And the other bands wouldn't be so good, the ones that are on Earth satellites.
So the short answer is I don't know, because I'm not on the team and I'm not privy to whatever decision making went into that. I can tell you that Magellan was an S-band radar. There is currently one thing we haven't talked about at all yet, and I know we could talk for hours, because if you start me, I will continue talking until you cut the Zoom off. Right now, there is another potential Venus mission in the works. Across the pond, the European Space Agency is about on probably Wednesday. We're expecting this coming Wednesday. We're expecting to hear the outcome of a multi-year effort to characterize and select their M5 mission. So whereas NASA has Discovery, New Frontiers, and Flagship are sort of the 3 levels of increasing cost in planetary missions, the European Space Agency doesn't break things out by planetary and astro and helio. They lump everything together, but they have S, M, and L missions, small, medium, and large. And their medium class missions are comparable to New Frontiers, which is NASA's 850 million kind of thing, a little bit less than that for ESA. Their M5 call, I don't know how many they started with, but they ended up shortlisting. Often how these things work is you might get 20. Like in the case of DaVinci Plus and VERITAS, there were about 20 missions put in. In February of last year, that was narrowed down to 4. Those 4 teams were given about $1.5 million each to really fully refine their project proposals. And then we had the selections on Wednesday. I don't know how many there were at the beginning. 3 missions were shortlisted about 3 years ago for a longer, what we call a pre-phase A. Last year, one of those 3 missions was taken out of contention. It was deemed to be too expensive, wouldn't be able to make that cost cap. And the 2 remaining missions, like I said, ESA doesn't break things up by planetary and astro. One is a deep space telescope looking at high Z values way back when, called Theseus. And the other mission is called Envision, and it is a Venus radar mission. And we are going to hear on Wednesday which of those 2 will get picked. Now, you might ask, well, we already have VERITAS as a radar mission, and why would we want to send Envision? Well, that's never stopped us sending Mars Reconnaissance Orbiter, Mars Odyssey, Viking, Mars Express, Mars Orbiter mission. How many missions at Mars have cameras? If you go to a planet, you bring a camera, regardless of what your overarching science objectives are. If you go to Venus or Titan, you have to bring a radar. Envision would carry an S-band radar. It has a different science focus and a different purpose than VERITAS. There's huge complementarity, but not the same thing. So it's like I'm going to bring an infrared camera on this mission. I'm going to bring a visible camera on that mission. The X-band radar has a particular function. It's got a particular capability. It has particular power and mass requirements that allow VERITAS to be competitive within the discovery cost box, which is about $500 million, which objectively is a lot of money, but in space exploration isn't really for ultimately a 20-year mission. So the idea is X-band was chosen to be the best thing for VERITAS. If Envision flies, it will probably carry an S-band radar. And one of the reasons why that's exciting is because that's the same kind of radar Magellan had, which means you could directly do apples to apples. You could downsample the resolution of your Envision data and do a direct comparison to look for change between Magellan and Envision, right? Wow. And of course, there are other synergies I can't even think of to having 3 missions operating around the same time around this one planet. So. Yeah.
I completely agree with you. There's no reason not to have multiple missions. Complementary instrumentation can be sent. These missions aren't built in a vacuum, and they're not built right now. These were the proposals to build the spacecraft, and there's always tweaking that's done along the way. So if the Europeans approve their mission, scientists in Europe, scientists here, we'll talk and say, wow, if you do this to yours, we can do this to ours, and then even more science is done.
That's exactly it. Exactly it. Yep. So and we're hoping to see that. We're hoping to see this Venus ecosystem develop now, where these teams are communicating.
Yeah, it's exceedingly exciting times. Venus has been ignored more than 30 years now. It's time to go back, and we are. And what year do these missions launch, provided all goes well? Of course,
all goes well. I'll need to go and check this for sure. It's something of order 2028, 2029, and if Envision is selected, it goes in 2031.
Yeah, I thought it was something like that too. Oh, my cat's getting on my mouse here trying to mute my own audio. That would be bad. Well, thank you so much for joining us tonight. Wonderful speaking with you. Like I said, once we're back in person, and folks, that's going to happen sooner than you might think. We'll make announcements as we know more about when we can reopen. Again, foundation members, feel free to join our foundation, and you'll get invited to come see Griffith Observatory in person on June 18th. That's right, we're going to have a member event before we reopen to the rest of the public. You can come in, see the Samuel Ocean Planetarium, the Leonard Nimoy Event Horizon Theater, see all our wonderful exhibits and all our halls, see what we've done to some of those exhibits to update them, and just enjoy the observatory, take a look through a telescope. And thank you so much for joining us tonight. Thank you, Paul, Dr. Paul Byrne, again, from North Carolina State University, a real expert in planetary science, and we're going to keep you on our list of people to talk about as these discoveries are made. So
you bet. There's a lot more Venus to talk about.
Yeah, absolutely. And thank you so much.